Hello again. In the previous video, we kind of went over the original design of the charging and load distribution system. In the old Chrysler products, early 60s through mid 70s, ammeter based, ammeter in the dash, charging current routed through the ammeter so we can monitor charge rates. We also went over the fact that splice 1 is the primary load distribution, and it is on the alternator side of the ammeter. So that means power created by the alternator provides power to the loads, all taking place on the alternator side of the ammeter, and it will not register through the ammeter. We only see charging current when the system is in operation. If the alternator is not functional, then we're going to see a discharge current. What we want to do now, this is this harness that I'm using for this demonstration is in somewhat good condition. No real obvious issues with it. So we're going to take a closer look and see if we can find any issues with it, any resistance. We're looking for resistance that would create heat. So we're going to look for resistance, and the easiest way to do that is through a voltage drop. You can actually measure at various points in the circuit where you may be losing voltage. At this point, we have the alternator powered up. We're running about 14 volts over there on the alternator output. Charging the battery at less than, 4/10 of an amp there. Let's take some measurements around a few points on this system and see if we can find some voltage drop. In order to do voltage drop tests, you got to have some current flowing. So let's turn our high beams back on again. It's worth about 12, 13 amps. You can see that over there on that ammeter. You're not going to see it on this one because it's being consumed again on the alternator side of the ammeter, and it's not going to show up. There's half an amp of current flowing through the ammeter currently charging the battery. Let's see if we can find any voltage drop. We'll start with the battery bus here. The battery bus feed. This guy comes from splice 1. There's 0.2 of a volt we're losing between this point and the alternator output stud. So that would include the Packer terminals on the alternator feed, the black wires here. Splice 1 back to the red to here. From here, let's go to the headlight switch and see what we got going on at the headlight switch. Now we're lost another 0.1 of a volt between splice 1, where this guy's getting the power, and the headlight switch. Let's just jump over to the lights and see what we got going on here. Almost 2 volts at that point in time we're losing. So somewhere between the lamp load here and the power source, we're losing almost 2 volts of voltage. And what becomes of that lost voltage? It's being converted to heat somewhere, and we're going to see if we can have a look-see, see if we can find out where that's happening. Stand by. Turn on some headlights. Again, about 13, 14 amps. Alternator is functioning. This would be simulating engine on. So our power should be coming from an alternator over here. And we're already seeing some wire warming going on. This bunch of wires again is our headlight stuff. Headlight switch. 16 gauge wiring in the dash harness that runs down to the dimmer switch. The dimmer switch is down in the corner here. and then our high beam lead that runs out to the bulkhead and runs out to the wire that actually runs out to the lamps out there. This is the alternator feed. You'll see some heat starting to form there, and you'll see this is the corresponding bulkhead connector terminal, black wire that comes down here and feeds splice 1. Splice 1's right there somewhere. From splice 1, our headlight switch comes off of black with a white tracer, 12 gauge. That's this guy in the back of the switch. Down in the corner here, that's an illumination light that's on. So you're seeing a bulb heat here, but that doesn't have anything to do with what we're looking at. In a second, we're going to move our target over here and see if we can get some numbers off of those Packard terminals as they heat up. So we're at 90 degrees already on that alternator feed Packard and climbing. We're already 116, 117 right there at the headlight switch. That light green, that's the light green wire that feeds the dimmer switch, and that's down here. This heat, by the way, is the dimmer switch connector, which it looks to me like there's some issues there. But we're going to cover headlights specifically in its own video, headlight relays, and how we can resolve this. At this point, we're just watching our charging system. You'll see the alternator wire is now heating up a little bit more. Showing 80. Oh, this is starting to fall off now. What we've done here is shut off the alternator, and current is now being provided from the battery, and you'll notice that the battery feed wiring is starting to warm up. That's this upper one here. That's the red wire that runs over to the ammeter. Actually it routes this way, follows along here, comes around the other side. This is the battery side of the ammeter. And the black wire comes back out of the ammeter and goes to splice 1. In this case, the load is over here on the headlight, so that black with a white stripe again, back over the headlights. But you'll see that the battery side of the charge circuit is starting to warm up, and its bulkhead connector. Bulkhead connector terminal is starting to heat up. And again, this is stock headlights, or somewhat stock headlights, 14 amps. So that kind of explains where we're losing that voltage. Almost 2 volts getting lost through that wiring in those terminals. We'll get into the headlights and talk about ways to fix that, but at this point I think we're going to lead into getting back to the stock wiring, and we're going to up the load a little bit. We're going to use that carbon pile tester and add some more current to this system. See what really happens. Okay, after looking at the infrared camera's image of this system with some current flowing, it's pretty clear we've got some heat being generated here. Good portion of it's going on over here in the headlight wiring. Kind of indicate that these wires may not be big enough for those lamps, for that load. You also saw some heat going on here at the dimmer switch, the high-low switch. It looks like the connections here were a little bit kind of screwy. But that's a problem. We're going to get into the headlights in another video. At this point, we're going to stick to the power distribution and charging system. We also saw some heat going on here on these Packards. We kind of looked around some of these other connections to see if we had any significant heat going on. Looked specifically at the ammeter, didn't really see a whole lot going on there. These have good tight connections, original ring terminals. Insulators are in good shape. Not really an issue for the 14 amps we were looking at there. I think maybe the next step here would be to up the load somewhat. And in order to do that on this demonstration, I have to provide loads externally. Let's get set up for that, and I'll show you how this system performs with some more loading. Stand by. All right, now we're going to add some more loading to this system that we can't get out of the stock loads. We're going to do that with our carbon pile battery tester. I have my load attached to the unswitched battery bus at the fuse box, again running to splice 1. So we're going to put that load on splice 1. Alternator is operating over here, so we're going to see that current come from the alternator. Now, another warning, this particular variable resistor is not real precise, so we're going to experiment and get where we want. I think I'm going to take her up to about 25 amps or so, maybe 30. We'll keep going here, hang on. Should be able to get some more current flowing than we could get from those headlights. There's about 30 amps verified here on this analog. You also see it here on the analog. Yeah, actually, this shows 32. Yeah, we're up a little bit. Okay. I'm going to get an IR image of this as well, but let's take some voltage drop measurements. 13.38 I got over here, 13.4 on that. And just between the alternator output and the battery bus, splice 1, we're losing 0.73 volts. So through this wire connection, through the splice, through that Packard, the black Packard is the alternator output. We're not doing anything with the battery. There's like 3 amps going on over here. But we've got, now we're creeping up to 40 amps over there on the alternator output side. And I see my power supply is just redlined, so let's back that off a little bit. Get back to 30. This time we're going to do the same load test, but we're going to do it with the alternator off. So this would emulate a high current with the key off, just sitting still somewhere. Now we're going to get our power from the battery. The power supply to splice 1 is going to take a different route to get there. It's got to go through the ammeter to get to the battery. Let's crank up some current. Again, we're going to take an IR image of this as well and pop it up there, but so there's 29 amps coming out of the battery. We have a pretty good discharge indication. While we're at, let's just see what it takes to full scale the ammeter. Full scale on the ammeter is roughly 50 amps. You can see it over there. I'm going to back off though, that's a little too much for what we're trying to do. Keep it around 30 amps. Now, again, I'm going to take an IR image of this as well. But at this point, we shouldn't see much buildup of heat on the alternator side. We should see it on the red wire. This guy should, and it is, I can tell already, but I'll get the IR image out. Not much going on here at the ammeter. Nothing at the terminals. So that pretty much puts this system at a pretty high load. We should be able to see where the issue is there now if there's any issues with the stock setup. Let's check our voltage drop with power coming from the battery. 1.12 over here. So we're losing a good little over a volt between the stud on the starter relay and splice 1. So that would be Packer terminal, ammeter, splice 1. Let's take a quick measurement here on the Packer terminal. 0.25. Yeah, we got some smoke going on here, so we're gonna throttle her back, cream up to 40. So that's an issue. As a review, we're talking about the Packer terminal, this guy, the red one. Black one is the same connector going out to the alternator. So there are two of these Packards in that charging system. The main difference in current between the two different Packard terminals is that for most of the time the vehicle's in operation, most of the load currents being consumed at splice 1 and the charging current going to the battery are taking place on the black wire. And the red wire will handle charging current for the battery and any of these loads to splice 1 when the alternator is not functioning, not in operation, the car is sitting still. Typically, vehicles with higher electrical demands, electrical options, air conditioning, power windows, power door locks, so C bodies, typically. On the other platforms, those are all options. But you have a high option car, all consuming power from the fuse box or through the switched. The switched loads are also getting power from splice 1. Red wire. Turn on your accessory. Most of that stuff is on the accessory side of that. The black wire. Doesn't matter. The power source is here. And the more electrical loads, the more you're going to depend on power coming from the alternator. That black wire is going to be a problem for high option cars. And again, that's the C body typically, and that would lead into something called the C body recall. And we'll talk more of that on another video when we talk about some fixes to some of this stuff. But this is just to point out that the system does have a weak link, and it's the bulkhead connectors in the charge path. There are some who think the ammeter is the big deal. It's not my experience. If the ammeter connections are maintained correctly, they're not allowed to get loose. If they're mishandled, abused, twisted, left loose, insulators damaged, we're going to have some resistance issues here as well. But the original design, the ammeter is not the cause of these issues. We'll move on. We'll get some IR images of this, and we can look at some heat, and we'll talk about it. Okay, looking at some temps on our higher load at the battery with the alternator not functional. We got some temps going on here on that battery feed. That's the fusible link there, by the way, that's warming up. This is the battery feed here. I had shut off the alternator, but I see the alternator wires are still a little bit warm there. But the primary path without the alternator is through that ammeter. A little bit of wire warring going on there. There's an indicator light in very close to the ammeter there that's also throwing us off on these numbers. That guy right there. We're up 200 degrees on that battery feed Packard there. I mentioned earlier there was some smoke, and again that's 30 amps. Next test, we're going to move our load over to the battery, and we're going to load test the entire charging system. Alternator is powered up. We're currently charging the battery at 3.5 amps from that last test we did that kind of pulled the battery down a little bit. A little deflection going on here on the ammeter towards the charge side. We're going to get that 30 amps to flow through the entire charging system by putting the load at the battery. This is another good way you can load test your charging system, see if your alternator is up to snuff. But at this point we're going to do some IR imaging here. So let's dial in about 30 amps here. There's about 30 amps, and it's flowing through the entire system. You can see that what I call false charging. And it's not really charging the battery. It's, as far as the ammeter is concerned, the current is flowing that direction. It thinks it's charging, but you're adding current stress to all these wires. Let's get some IR images on that. Yike. I'm looking at it as we're recording. I'll show it to you. But more importantly, I'm seeing 250 degrees at that red Packard right now. I'll show you the images. It might be on this same. I haven't figured out how that's going to work yet. It might be a windowed picture in this video, but we got some heat building up over there. That's the carbon pile starting to heat up too. So we got some wire warming here. Oops. Too much heat for that guy. Oops, we're still cooking over there. I don't know if you can see it, but they're smoking. We're smoking that wire. In any event, the stock system is limited on its ability to handle any significant current. But it also, you put load on it like this, it's an easy way to find out where the weak spot is. So some of the next videos we're going to start talking about how we can fix things, make things better, handle more current. We're going to try to do stuff about how the factory dealt with some of this, some of their approaches. The C-body recall, as I mentioned, the fleet bypass is another one that was a factory attempt to address this weakness. And then we'll start talking about other modifications we can do to go even further with this system. These days we like our electrical accessories, and they consume power. We'll talk about larger alternators and what we got to do to the wiring to support that, and load placement issues. Where we put loads on this system does matter, as we just saw. We can't be adding things to the battery without creating issues here. That was something that was done quite often back in the day, actually. A lot of the police radios and accessories on the fleet production wound up with high current radios, and everything was hooked up to the battery. You really needed that current to run the radios. But it messed with the charging system, as we discovered here.